at that point, the boundary condition will be dt by dx equals 0 and the left surface. On the right surface, there will be still the same boundary condition. And with different boundary condition, you will obtain, say, different values for C1 and C2. The equation is the general solution is still the same, right? Because the heat equation is still the same. But the boundary conditions are different. And then you will get a different solution. Basically, say, for this case, now you have boundary conditions, say, only the right hand side, you have this equation. And you have one more condition that's basically if you look at that case, this is insulated. Okay, this surface is insulated, and we actually choose this point is x 0 for x, and this is still L. The surface is still x equal L, and we have fluid this side. This side is actually insulated, and you then have boundary condition at x equals 0. You have the boundary condition that is dt by dx equals 0. That's for insulated surface. And at x equals L, we still have the same boundary condition, which is minus k dt by dx at x equals L. Still, say, assume that heat actually is transferred to the fluid, or in the x direction. So you have h, that's the convection coefficient, the T surface, the surface of the temperature of the surface, temperature of the T surface, minus T infinity, that's the fluid temperature. And now you have, say, two different boundary conditions. And the solution is still the same. That's T equal minus Q over 2K x squared plus C1 x plus C2. And you still have, now, you have another equation basically is x equal L. Temperature is T surface temperature, because you assume it's surface temperature. Now, from this, then you have three unknown parameters. That's Ts, C1, C2, and you have three equations, 1, 2, 3. So you can solve for Ts as well as C1, C2, and then you basically have temperature distribution. That's for this case. And that's for plain ore case. You will find out that the temperature distribution, the final temperature distribution is actually you look at loads. I give the solution loads, especially the temperature. Actually, yeah. Not even. Okay, so you can try to, I think you can try to find the temperature distribution, find out the solution yourself from these, say, three equations, four equations. Basically, you find the C1, C2, that's the distribution. That's for plain ore. And similarly for, actually it's quite similar for, say, cylindrical system or spherical system. It's exactly the same. It's just starting from the equation for cylinders, for spheres, and and then do the same thing. But one thing I want to say, stress is that for cylinder, if we look at cylinder case, at least you have a cylinder, okay, and you have heat generation inside cylinder. This could be basically a nuclear reaction case. So you have material actually generating heat inside the material, and then that heat will be, and that material will be cooled down by cold fluid surrounding the material, cylinder, and then you can find that starting from that heat equation for cylinder, you can actually simplify that problem to this form. It's quite similar to the equation for potassium coordinate. And then you have the boundary conditions, right boundary conditions. Now, in this case, say, as you can write two boundary conditions. One is that actually it's the middle or center of the cylinder, and the other one is the surface of the cylinder. You can imagine that in the center of the cylinder, there should be no, in the center there will be no heat generation or no heat storage or that sort of thing. Because that's in the middle, because it's symmetrical. So you have a boundary condition in that case that's dT by dr is 0. That's the boundary condition for the center of the cylinder, center line of the cylinder, central line. And then the surface condition, you could have, say in this case, you have a typical convection condition. Basically, it's the same as the condition that I show you that you actually apply heat balance on surface, outer surface of the cylinder. You see that heat conducted from the to the surface should equal that heat convection between the surface and the fluid. And you can write that equation, but you have to write that in cylindrical coordinates. Or you can say define the temperature surface, the outer surface temperature, Ts. And then you could solve that heat equation for cylindrical coordinates, and then find that temperature division in that form. Basically, you integrate twice, you get this. Then integrate once, you have this. The second time, integrate the second time, you have this temperature division. And then apply boundary conditions, then you have the solution, the temperature distribution for a cylinder. And now because you use the surface temperature Ts, you assume the temperature Ts, but you don't know the temperature Ts yet. So what you do actually, you apply heat balance over the whole material, and then use that whole material, because heat is generated inside the material, the cylinder, and that's the total heat generation inside the material. And that heat will be say transferred by convection, completely by convection. And so that's HA times Ts minus 250, and A now is the outer surface area of the cylinder, because heat is actually transferred across the outer surface, and that's 2 pi r times the length of the 2 pi r is times the length of the parameter times the length of the cylinder. That's the total surface area, and then you can then find out the Ts, and then you then plug that into the solution. Then you have the temperature distribution for the cylinder.